What if I told you that gravity doesn't just pull on space, it pulls on time itself? In 2025, this isn't speculation. Satellites like those guiding GPS must correct for time running faster in orbit by microseconds each day, while Earth-based atomic clock experiments can now detect subtle differences at scales as fine as 1 part in 1017 per second across just a few millimeters of height. These results suggest that gravity continually warps the flow of time, even in ordinary conditions. But if it can stretch something as fundamental as time, what else about gravity refuses to make sense? Gravity's strange weakness. It seems almost absurd at first glance. The entire Earth, so massive that it can hold down oceans, drag the tides with the moon, and keep a satellite speeding around its orbit, also pulls on you every second of your life. You breathe air it holds in place, you walk under its steady tug, and you quite literally cannot step outside its reach. And yet, with barely a thought, you can lift a mug of coffee in your hand, casually overcoming that planetary pull as if it were nothing. How can the same force that governs whole planets and moons feel so flimsy in daily life? This tension, between weakness up close and dominance across the cosmos, sits at the center of gravity's mystery. Physicists make this puzzle even more striking by comparing gravity to the other fundamental forces of nature. Electromagnetism allows a small magnet on your fridge to beat the pull of the Earth beneath it. The forces that bind atomic nuclei together are so much stronger still that gravity barely belongs in the conversation at those scales. In fact, among the 4 known forces, it is easily the weakest, dozens of orders of magnitude weaker than electromagnetism or the nuclear forces at the level of particles. And yet, when you expand the view to planets, stars, and galaxies, gravity takes over everything. The reason lies in how it behaves. Unlike magnetism or electricity, which attract and repel and often cancel one another, gravity only pulls. It accumulates without limit, stacking one contribution of mass on top of another, until the weak becomes overwhelming. That's why in the very same universe where a paperclip can outwit Earth's pull by snapping toward a magnet, vast structures of stars form only because of gravity's quiet persistence. But even defining gravity's strength turns out to be harder than it sounds. Scientists give it a formal name, the gravitational constant, known as G. That one number underlies Newton's law of gravitation and Einstein's equations of general relativity. We can measure the charge of an electron and the speed of light down to extraordinary accuracy. But with G, the results remain surprisingly slippery. In laboratories today, high-precision torsion balances, sensitive instruments that measure tiny twists from gravitational attraction, continue to return slightly different values than quantum methods that track the interference of falling atoms. These shifts are small in absolute terms, but the inconsistency matters. Cosmological models rely on G, yet its measurement still refuses to settle to the certainty we expect from such a fundamental constant. This is startling when you think about it. We can estimate the lifetime of unstable particles more precisely than the pull that holds your feet against the ground. Researchers carefully shield their setups against vibrations, drifting temperatures, and even distant earthquakes, and still they report outcomes that do not fully agree. Laboratories across Europe, Asia, and North America all push limits of precision, but no single number emerges unchallenged. These differences don't mean gravity itself fluctuates. They point to how close we may be coming to the limits of our measurement tools, or perhaps to some subtle feature of the universe not yet understood. Gravity hides in plain sight, yet refuses to be pinned down. And that brings us back to the paradox of its weakness. How can something that loses so easily to a magnet's pull end up controlling the fate of stars and galaxies? The answer lies in its persistence. Gravity may not cancel, screen out, or flip direction. Every added mass strengthens its pull, and the larger the system, the more those feeble contributions add together. Over billions of years, that slow accumulation becomes the architect of structure itself, spiraling galaxies, clusters bound across millions of light years, and great cosmic webs stretching from one end of the sky to the other. If magnetism behaved the same way, always amplifying without opposition, the universe would look unimaginably different. Instead, only gravity gets that role, weak in the laboratory but supreme across the heavens. That contrast plays out in our daily lives as well. Astronomers use gravity's faint signature to trace the outermost orbits of stars at the edges of galaxies, while engineers account for its relativistic effects to keep satellite-based GPS systems accurate to within meters. Both examples come from a force that barely resists when you stand up from a chair. It seems to wear two faces, negligible when stacked beside the other forces of nature, yet irreplaceable when gauged across astronomical scales. So the million-dollar physics puzzle isn't simply, why is gravity weak? But how does such a weak actor end up as the universe's architect? Physicists suspect that solving that question could highlight the bridge we've been missing between Einstein's spacetime picture and the quantum world of particles and fields. For now, though, the paradox remains open. And if gravity's fragile strength can already baffle us, its other defining feature raises an even stranger puzzle: its ability to bend the steady rhythm we call time. The force that bends time. We usually picture time as steady and absolute, the one thing in our lives that never bends. A wall clock ticks off seconds in New York the same way a wristwatch does in Sydney. Phones and computers sync without hesitation. It feels universal, insulated from anything else going on in the world. Yet when physicists learned to track time with extraordinary precision, they uncovered something deeper. Time itself is not fixed. Its passage depends on position, motion, and most of all, on gravity. No second is truly the same everywhere. This becomes clear in experiments that compare clocks at different heights. On the ground floor of a building, a clock ticks imperceptibly slower than one a few meters higher. For decades, we couldn't detect such minute offsets, but atomic clocks changed that. By 2025, their sensitivity had reached the point where researchers can measure differences at the scale of about 10⁻17 seconds across a vertical gap of just 1 millimeter. That means lifting a clock by less than the thickness of a paperclip registers a timing change. It is a spectacular confirmation of Einstein's prediction that gravity alters time at every scale, no matter how small. These shifts, though vanishingly tiny in human terms, are critical to the technologies we rely on. The Global Positioning System is a prime example. GPS satellites carry atomic clocks that run in orbit where gravity is slightly weaker and motion is extremely fast. Without adjustment, those orbital clocks would drift by about 38 microseconds each day compared to Earth's surface. That doesn't sound like much, but even half a microsecond of error translates into hundreds of meters of misplaced location data. To make GPS accurate, engineers must constantly apply relativistic corrections. In effect, the technology guiding everything from smartphone maps to aviation navigation depends on acknowledging that gravity and motion reshape time itself. The principle behind these differences has a formal name: gravitational time dilation. It states that clocks closer to large masses tick more slowly than clocks farther away. Gravity pulls not only on matter, but on the very progression of events. The deeper you sit in a gravitational well, the more your seconds stretch compared to those above. The effect is faint on Earth, yet becomes more striking when you leave the surface. The International Space Station presents a clear case. Orbiting a few hundred kilometers above Earth, astronauts experience weaker gravity than people on the surface. That would make their clocks run slightly faster. But at the same time, they are circling the planet at over 7 kilometers per second, and high velocity causes time to run slower. That second effect, known as kinematic or velocity time dilation, partly cancels the gravitational difference. The outcome is subtle but measurable. Their clocks tick at a slightly different rate from ours, shaped by both influences at once. Scientists must account for each factor carefully. Otherwise, comparisons between spaceborne and earthbound experiments would fail to match theory. It is striking to think that such incredibly small shifts can be seen so plainly in data. Two clocks synchronized on the ground but then separated, one placed on a mountain, the other left below, will no longer agree when brought back together. Move one into orbit and the divergence only increases. The lessons drawn from black holes or cosmological expansion apply right here, in the way an atomic clock ticks when nudged upward by a millimeter. What all of this teaches is that time is local. There is no single universal rhythm governing the universe. Instead, every region, every altitude, every state of motion sets its own pace. From laboratories demonstrating a fractional difference across paper-thin distances to satellites proving the necessity of microsecond corrections, the evidence is overwhelming. Gravity doesn't just govern falling objects, it governs the tempo of time itself. Seen from this perspective, gravity stops looking like an invisible rope dragging objects downward. Instead, it shapes the very arena in which events occur. The path of a falling apple is not dictated by a pull, but by a curve in spacetime that lays out its natural trajectory. Time and space are woven together, and gravity is the feature that warps both of them at once. The payoff is simple but profound. Clocks reveal that time is not absolute. Gravity alters it, velocity alters it, and we have measured those changes across scales ranging from laboratory benches to orbiting satellites. Without these corrections, our most precise technologies would falter, and our understanding of the cosmos would collapse. And if gravity can bend time in this way, it hints at an even stranger truth. Its influence does not stop there. The same framework that distorts moments also reshapes the geometry through which everything moves. When space gets twisted, gravity shows its most curious behavior when it twists the fabric of space itself. Unlike magnetism or nuclear forces, which act directly on particles, gravity reshapes the background in which all motion occurs. It doesn't simply pull, rather, it alters the geometry so that objects, whether massive planets or even massless light, follow paths written into the structure around them. The orbit of Earth around the Sun is nothing more than a trajectory inscribed by this geometry. A constant balancing act along curved space itself has set in place. The clearest way to see this is by watching light. Photons carry no rest mass, yet they cannot escape the bends carved into space by mass and energy. A beam skimming the edge of a galaxy cluster does not trace a straight line through the universe, but arcs along the warped contours it encounters, like water flowing around hidden terrain. From Earth, such deflections change how we perceive distant sources. Stars appear shifted, galaxies stretched, and sometimes a single quasar multiplies into several distinct images. What seems like an illusion is really the structure of spacetime bending the path of light itself. This phenomenon is known as gravitational lensing. The name recalls lenses of glass, though no physical medium sits between us and the distant source. Instead, mass alone, stars, galaxies, or whole clusters, distorts the underlying fabric. Predicted in Einstein's early work, lensing moved from theory to firm measurement over the past century, and today it is one of the most powerful practical tools in astronomy. By 2025, space-based telescopes had reached resolutions fine enough to capture thousands of Einstein rings, circles of light produced when a distant galaxy or quasar aligns almost perfectly behind a massive object in the foreground. Survey teams now catalog tens of thousands of these warped arcs, each etched into the deep sky like a trace of hidden structure. The importance of these distortions lies not only in confirming Einstein's equations, but also in the way they serve as maps. Every angle and arc encodes information about the matter responsible for bending the light. Where galaxies cluster more tightly, the bending strengthens. With precise measurements, astronomers turn these patterns into what they call mass maps, detailed reconstructions of where matter sits, even when no light gives it away. This includes the elusive dark matter, invisible except for the way it alters spacetime. Thus, lensing transforms beams of light into guides that chart the unseen universe. The 2025 surveys also revealed subtler effects. In wide-field images, entire swaths of faint background galaxies appear stretched into smeared arcs, their shapes betraying concentrations of foreground mass. In strong cases, one source splits into multiple copies, each arriving along a different bent path. Less dramatic but far more numerous are small distortions sprinkled across every image. These weak lensing signals accumulate statistically into another kind of map, one that shows the invisible scaffolding of matter spread across billions of light years. The match between observation and the predictions of relativity continues to stand out. The bends, however faint or dramatic, fall exactly where Einstein's equations say they should. For us as observers, this creates a striking realization. We never see the universe unfiltered. Every photon arriving at a telescope has traveled along a path sculpted by intervening matter, large or small. Einstein rings and dramatic arcs are rare highlights, but even empty-looking patches of sky hold countless tiny deviations. Deep-field images taken in 2025 made this plain. Thousands of miniature lensing signatures emerged, each recording the effect of spacetime drawn taut or curved by ordinary galaxies, by dark matter halos, or by other unseen concentrations. The night sky we admire is not a flat backdrop, but a textured, twisted surface where every massive object leaves its imprint. What makes lensing so valuable is its dual role as both phenomenon and tool. It confirms the geometric vision of general relativity, while at the same time giving astronomers a method to weigh clusters, trace dark matter, and magnify distant galaxies too faint to be noticed otherwise. Background galaxies, stretched and brightened by natural cosmic lenses, suddenly enter reach of our detectors, carrying light that would otherwise be lost to time. In that sense, gravity provides not just limits but opportunities. Weak in everyday life, it becomes a cosmic magnifier on the largest scales. Those warped arcs are not just striking images. They let scientists map dark matter and detect whole structures that emit no light at all. And yet, for all its elegance, gravitational lensing reveals only part of the story. It shows how mass bends space and diverts light, how galaxies and clusters sculpt the larger web of the cosmos. But if light can be deflected and magnified, what happens when gravity is pushed even further? When spacetime becomes so contorted that not even light can slip away? That is the question pushed to the limit in the study of black holes, where gravity rules alone and spacetime itself is driven to extremes. Black holes, where gravity rules alone. A black hole is defined by a single radical fact. Once matter or light crosses its boundary, nothing comes back. That invisible boundary, called the event horizon, marks the point where escape would require a speed faster than light. Unlike stars or planets, which simply bend spacetime around them, a black hole compresses mass until spacetime closes incompletely. What remains is not just an object of immense density, but a region where known physics reaches its limit. For astronomers, however, black holes are less about the unreachable interior and more about the signals we can detect from the outside. When two black holes spiral together and merge, they send out gravitational waves, ripples of spacetime moving at light speed. These waves stretch and squeeze space as they pass, changing measured distances by amounts smaller than the width of a proton, but sensitive detectors can still record them. In 2025, new data releases from the LIGO-Virgo, KAGRA, LVK collaboration expanded the gravitational wave catalog, known as GWTC40. Among the highlights were high-mass merger events, including GW231123, which pushed the upper end of the known black hole mass range. Each new entry gave clearer tests of relativity under conditions impossible to reproduce elsewhere. From a gravitational wave signal, researchers can infer the mass of the black holes, the spins of each object, their distance, and even the orientation of the merger. Those numbers tell us whether Einstein's equations continue to predict the observed behavior, and so far, every result has remained consistent with general relativity. At the same time, the data give us a more complete picture of the population of black holes in the universe. Stellar remnants a few times the mass of the Sun are confirmed. Supermassive giants millions to billions of times heavier dominate galactic centers. And now, the intermediate range has begun to fill in with candidates confirmed through mergers. The discovery of these mid-sized black holes matters because it connects the endpoints of the spectrum. If small remnants from collapsed stars can gradually combine through repeated collisions, they may grow into the seeds of the enormous black holes we see at the cores of galaxies. This continuous range of masses was once speculative, but gravitational wave astronomy is now demonstrating it with real events. Each detection refines our understanding of how galaxies themselves may evolve over billions of years. The power involved in these mergers is nearly beyond comprehension. In their last seconds, colliding black holes can release more energy in gravitational waves than an entire galaxy emits in light over the same interval. Yet these waves travel across space with almost no interference, bringing us an unblurred record of the event from billions of light-years away. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves arrive carrying information about the collision in its purest form. That clarity is what makes them such useful probes of black hole physics. But there remains a divide between what we can measure with great confidence outside and what resists explanation on the inside. General relativity describes the geometry just beyond the horizon with remarkable accuracy, and gravitational wave detections continue to confirm it. Yet the theory breaks down at the singularity, the mathematical feature inside a black hole where density and curvature seem to become infinite. Physics does not handle infinities well, and the very appearance of them signals that our frameworks are incomplete. Relativity paints one picture, quantum theory demands another, and neither can currently describe the reality at the core. This tension is why black holes are so critical to science. They are natural laboratories where gravity is pushed to extremes, allowing us to check whether existing theories hold or whether subtle deviations point to new physics. Every recorded merger becomes another opportunity to check parameters such as how fast spacetime ripples spread, or whether the polarization of the waves matches predictions. Any departure would hint at cracks in relativity's grip, but so far, Einstein's model continues to pass at scales he never imagined. Speculation about what actually happens beyond the event horizon continues to range widely. Some proposals suggest that spacetime does not collapse to an infinitely small point, but instead halts at a quantum-defined core, perhaps in the form of a new state of matter or a fundamental graininess of space itself. Others argue that black holes may eventually reveal links to entirely new physical frameworks, ones that unify quantum theory with gravitation. At present, these ideas remain unproven, but the very existence of black holes forces us to keep looking. What we can say clearly is this: we have the tools to map black hole populations across the cosmos, measure their mergers with extraordinary precision, and test Einstein's equations against data again and again. What we cannot yet explain is the interior, what really replaces the mathematical singularity, and how gravity works in that regime where quantum principles should dominate. This gap between external certainty and internal mystery is exactly what makes black holes more than astrophysical oddities. They are evidence that our best theories point the way but still stop short of a complete understanding. And so, we arrive at a frontier question. We can listen to the collisions of black holes across the universe, reconstruct their properties, and see relativity confirmed in detail. But when we ask what lies beneath the horizon, the answers slip away, reminding us that our theories overlap but do not yet unify. We can hear black holes merging, but what they hide inside still refuses to be explained. Why that divide exists is the central tension between relativity and quantum mechanics. The irony is that even as these mysteries unfold on cosmic scales, gravity's ability to bend time also reaches directly into ordinary life. It affects the devices we carry in our pockets every day, though we rarely notice. GPS and the billionth of a second problem. Imagine opening a map app and watching your position appear almost instantly, marked by a precise blue dot. That simple display depends on an intricate system of satellites orbiting Earth, broadcasting timing signals with astonishing consistency. This is the global positioning system, and its accuracy is tied directly to one of the strangest consequences of gravity. Time does not flow at the same pace everywhere. The problem goes deeper than technical fine-tuning. Without relativistic corrections, GPS would fail completely in a matter of hours. Each satellite circles Earth from about 20,000 kilometers above the surface. On board, atomic clocks record and transmit precise timecodes to receivers on the ground. Your phone or car does not measure distance directly. It compares the arrival of these signals from at least 4 satellites and calculates where the timing overlaps. In practice, the whole system works only because those signals arrive in strict synchrony. A discrepancy of even a few billionths of a second would shift a location fix by several meters. Consistency makes the difference between a working map and misleading directions. Relativity complicates this neat process. 2 distinct effects shift the ticking of satellite clocks compared to those on Earth. First, satellites experience weaker gravity at their higher altitude, which makes their clocks run slightly faster. Second, their high orbital speed slows the ticking down. These influences act in opposite directions but do not balance perfectly. The net result is crucial. Without adjustments, a satellite clock would get ahead of ground-based time by about 38 microseconds every single day. That difference, while seeming negligible, would produce errors that grow into kilometers of misplaced position within hours. This is why engineers must bake corrections directly into the system. Those microseconds matter because GPS tracking is inherently tied to the finite speed of light. A signal traveling from orbit to Earth races across tens of thousands of kilometers. Light covers that distance in a fraction of a second, but compare one clock running even slightly fast to another running slow, and the system immediately produces false distances. A 3 microsecond drift already corresponds to nearly a kilometer of error on the ground. Apply that logic to dozens of satellites broadcasting continuously, and the problem multiplies. By the end of a day without relativistic corrections, the blue dot on your phone could show you in the wrong city. From the start, designers accounted for Einstein's predictions. Satellite clocks are deliberately preset before launch to run slightly slower, so that once in orbit, they tick at a rate that aligns with Earth clocks after gravitational and velocity effects. But corrections do not end there. Once satellites are operational, ground stations monitor their performance constantly, uploading fine adjustments as needed. This coordination ensures that each signal, despite relativistic distortions, contributes to accurate triangulation of global positions. The level of refinement has only increased. In 2025, applications demand positioning accuracy within centimeters, not just meters. Modern satellites carry atomic clocks that track time to staggering precision, down to parts of a billion seconds. Yet even with such capable instruments, corrections remain vital. Factors as small as temperature shifts, subtle electromagnetic influences, or variations in Earth's gravitational field can affect the ticking rate. When accuracy is measured in centimeters, nearly every environmental or geophysical detail becomes significant. Engineers now incorporate corrections for long-term changes in Earth's mass distribution, including the effects of melting ice sheets, groundwater movement, and atmospheric patterns. What was once a system ensuring rough navigation has become a backbone of precision industries ranging from agriculture to construction. Consider the chain of dependencies. Aircraft navigation, autonomous vehicles, and cross-country transport corridors all rely on GPS-guided positioning that falters if relativistic corrections slip out of alignment. Civil engineers building bridges and tunnels track machines and survey layouts using GPS stations calibrated to within centimeters. Farmers plan planting rows and fertilizer application according to GPS coordinates guiding machines, as if they moved along invisible rails. Even national power grids and financial systems synchronize transactions against reference clocks tied to these satellites. Remove relativity from the calculation, and the infrastructure of the modern world loses its coherence. The significance of Einstein's theory here is striking. The same set of ideas that once seemed abstract, tested by careful observations of starlight bending during eclipses, has turned into a practical requirement baked into technology. Without acknowledging how both motion and gravity alter time, navigational systems unravel in hours. With those corrections, GPS becomes one of the most reliable and indispensable networks on the planet. This is not theoretical philosophy. It is how cities manage transport, how planes land, and how devices communicate across continents. Einstein's relativity may look like pure physics, but it functions as infrastructure. This dependence reframes how we think about time. Relativity reveals that there is no universal tick linking all places equally. Time depends on altitude, motion, and gravitational strength. The satellites above Earth experience hours just slightly differently than we do here, and their signals carry that information back constantly. Correction software reconciles those differences and delivers what looks like a simple digital map. Underneath, however, your device is running a continual negotiation with spacetime. Think about what that means. Without adjusting for those 38 microseconds per day, GPS would collapse into uselessness almost instantly. It is not just that relativity matters, it is that the satellites are engineered around it. Einstein's theory is not optional in system design. It is a critical piece of hardware logic. In effect, a modern smartphone quietly confirms relativity every time you use it to find a street corner. This perspective offers a sharper conclusion than any textbook could. The collision of physics and daily life is visible, not abstract. Satellite clocks are tuned because spacetime itself does not allow uniformity. If relativity were ignored, no phone could point you to a cafe, no financial system could guarantee transactions in sequence, and no pilot could rely on instruments syncing with Earth. As a result, every corrected second implies that physics rests alongside code and engineering. If there is a single takeaway, it is that relativity has already left the realm of theory. Global positioning does not just illustrate it, it runs on it. Crucial corrections fold into clocks, ensuring that the reality of curved spacetime becomes invisible to users who expect a blue dot to land exactly where they are standing. And that is precisely the point. Relativity is no longer distant physics. It is carried in orbit and reflected back into our daily movements. If we didn't correct for relativity, GPS would be useless in hours. So Einstein's theory is literally in your pocket. And this raises a natural question. If small distortions of time can ripple into systems we depend on every day, what happens when we track gravity itself on the largest scales? Dark matter's invisible grip. When astronomers track how galaxies rotate, the numbers refuse to balance. The stars at the edges orbit far too quickly for the visible mass, stars, gas, and dust to hold them in place. By Newtonian logic, galaxies should unravel, their outer stars drifting away across space. Yet they remain coherent, their spirals crisp and intact. Something unseen supplies the missing gravity. This unseen contributor is what scientists name dark matter. We see dark matter only via gravity. Its presence is inferred from motions and lensing, not light. It interacts neither through radiation nor absorption, leaving gravity as its only detectable signal. Over the past decades, evidence has piled up, but in 2025 the picture reached new levels of clarity. Wide-field telescopes, sensitive across optical, infrared, and radio windows, made overlapping measurements of how starlight bends across the sky. This bending, gravitational lensing, arises when mass warps spacetime itself. Light passing by massive clusters is offset, creating arcs, stretched shapes, or full Einstein rings in images. By analyzing these distortions across different wavelengths, researchers constructed mass maps. 2025 lensing surveys combine optical, infrared, and radio data to make detailed mass maps that repeatedly show more mass than can be accounted for by stars and gas alone. Every survey points in the same direction. Unseen matter dominates the gravitational budget of galaxies. The precision images leave little room for ambiguity. Clusters of galaxies, when mapped by light alone, suggest one scale of mass. When mapped by their gravitational bending of background galaxies, the figure jumps to several times larger. Whole halos of matter extend far beyond visible structures, envelopes of mass invisible to telescopes, but pulling strongly on everything nearby. Spirals like the Milky Way seem cocooned in vast halos of dark matter, holding the system together in ways ordinary matter cannot. Computer simulations of galaxy formation depend on these halos. Absent them, galaxies never stabilize into orderly disks, leaving instead loose swarms of stars. In reality, with dark matter halos present, galaxies gain the gravity needed to last billions of years. By 2025, astronomers pushed mapping even further outward, tracing not just individual halos but the filamentary scaffolding of the cosmic web. Deep surveys showed long strands threading across space, with galaxies clumped at intersections. These maps originate not in light but in lensing signatures, patterns across thousands of faint background galaxies stretched minutely along specific directions. When compared against large-scale simulations of how mass clusters through gravity, the resemblance is striking. Filaments predicted in theory line up with filaments captured in lensing surveys. Once again, the picture holds. Unseen matter outweighs the luminous and structures the universe at every scale. Still, the substance itself refuses to reveal its identity. It is not baryonic matter, the kind that makes up atoms, stars, or gas, because baryons would radiate detectable energy somewhere across the electromagnetic spectrum. It is not ordinary dust, which would scatter or obscure light. Instead, dark matter interacts with us only through gravity. Direct detection experiments deep underground have searched for particle collisions with sensitive detectors. Colliders have fired billions of high-energy particles in search of new signals. Direct detection experiments and collider searches have not yet confirmed a dark matter particle, so its identity remains open. The most straightforward candidates continue to elude proof. Nonetheless, with each year, understanding of its distribution grows sharper. Surveys of lensing fields reveal wide halos of dark matter, enveloping galaxy groups and clusters. Careful rotation measurements of large spirals confirm outer stars moving at speeds demanding more mass than starlight can explain. And at the largest scales, the geometry of the cosmic web anchors on filaments visible only in gravitational bending. Together, these strands form a consistent picture. Dark matter is not a minor detail, but the dominant scaffold for galaxy formation, cosmic clustering, and lensing distortions reaching billions of light-years away. This coherence of evidence makes the absence of a known substance more puzzling. We can place where dark matter sits, calculate its density, and watch its effect across cosmic history. Yet we cannot hold a sample or assign it to an identified particle. The balance feels odd. We map it with surfacing precision, yet its physical nature remains withheld. The situation affirms that gravity gives away its location but not its composition. At a practical level, this hidden architecture means that nearly everything visible is minor detail. Stars, supernovae, and interstellar gas are luminous traces superimposed on a greater skeletal structure of dark matter. Ordinary matter is the embellishment. Dark matter is the load-bearing frame. Without it, the universe would host scattered fragments, not interconnected webs. No spirals would stay bound. No clusters would cohere over billions of years. Gravity's authority at cosmic scales rests overwhelmingly in unseen content. What emerged in 2025 with greater certainty is not a new fraction, but a confirmation. Several times more mass resides in invisible form than in visible form. Surveys of massive clusters showed arcs where galaxies should not bend so dramatically, unless packed with unseen halo mass. Individual galaxies exhibited distortions consistent with vast reservoirs extending outward well past their luminous disks. Each piece adds confidence that the invisible not only exists, but surpasses the visible. This conclusion makes the universe easier to describe and harder to accept. Easier, because including unseen mass allows simulated galaxies to form exactly as observed. Harder, because the substance defies all instruments not based on gravity. No field detector, no radiation sensor, no particle collider has offered a direct confirmation. The scientific community knows where to point on a map, but cannot list what inhabits those coordinates. Dark matter, then, is not merely an astrophysical curiosity. It highlights the same puzzle physics faces with gravity everywhere. Gravity guides observation without exposing its underlying machinery. On Earth, it appears weak yet omnipresent. In space, it dominates through a material still undefined. The cosmos looks structured, but the weight responsible for that structure will not show itself except through gravitational signals. We can map where dark matter is. We still don't know what it is. That gap keeps gravity research urgent. And because researchers continually confront what gravity does without fully understanding what makes it act this way, they often ask a further question. If what we already see pushes our knowledge so far, what if gravity could act in stranger ways than attraction alone? Testing the possibility of anti-gravity. The notion that gravity might sometimes push instead of pull has fascinated scientists for decades. Gravity, as we experience it, is always attractive. Every object with mass pulls on every other. It never reverses its sign in any situation we can observe. Still, researchers continue to test whether there could be exceptions. The most tangible candidate is antimatter. If antimatter interacted with gravity differently than ordinary matter, falling more slowly, or repelling instead of attracting, the result would challenge the foundations of relativity and reshape how physics connects with the quantum world. Antimatter itself is familiar in broad strokes. For each particle we know, a mirror version exists, carrying opposite electric charge yet otherwise obeying the same physical rules. Electrons pair with positrons, protons with antiprotons, bring partners together, and they annihilate into pure energy. In collisions and accelerators, matter and antimatter follow the same laws, apart from the reverse charges. But the gravitational behavior of antimatter remains unresolved. Would an atom of anti-hydrogen, a positron orbiting an antiproton, fall toward Earth at the same rate as hydrogen? Or could a subtle difference appear, revealing that gravity distinguishes between matter and antimatter more than theory allows? By 2025, this question had moved from speculation into experimental research. High-energy physics laboratories began to produce and trap small numbers of anti-hydrogen atoms. These atoms are then cooled, confined in magnetic traps, and eventually released in ways that let detectors record their motion under gravity. Achieving this is extraordinarily demanding. The particles are delicate, annihilating on contact with ordinary matter, and extremely lightweight, so even tiny stray electric or magnetic forces can overwhelm gravity's faint effect. Shielding, calibration, and repetition are required to reduce interference. Laser cooling techniques and improved vacuum chambers have made it possible to hold anti-hydrogen long enough for meaningful testing. The principle being tested comes directly from Einstein, the equivalence principle. It states that in a gravitational field, all objects fall the same way regardless of composition. Drop a hammer and a feather in a vacuum and both accelerate identically. If antimatter were an exception, even by a minute fraction, it would violate that principle. Such a violation would not simply adjust a formula, it would demand a deeper framework. A repulsive or even slightly altered pull on antimatter would force a rethinking of both relativity and how it couples to quantum field theories. The outcome could stand as one of the defining revolutions in physics. So far, the research picture is cautious rather than conclusive. No laboratory in 2025 had confirmed anti-gravity. The most advanced antimatter trapping experiments indicate that anti-hydrogen falls downward as expected, within their still limited precision. These results suggest no sign of repulsion, but the precision is not yet sufficient to claim philosophical certainty. Physicists phrase the situation carefully. Current tests show no deviation from normal gravity within their error bars. That absence of evidence is itself a valuable step. It rules out broad classes of speculative theories, setting tighter numerical boundaries for what any new framework must respect. The work narrows possibilities even while retaining the chance that subtler effects might appear with finer instruments. The pursuit remains essential as much for the methods as for the answers. Pushing to measure gravity on antimatter requires instrumentation of exceptional control, magnetic fields that remain stable for weeks, detectors free from drift, lasers tuned with extraordinary precision. These improvements ripple outward. They support fields like quantum optics, particle physics, and precision metrology. Even if antimatter shows no gravitational difference in the end, the effort leads to technological gains and sharper tools that help drive physics forward in other areas. Importantly, speculation about consequences is now presented conditionally. If a deviation between matter and antimatter were ever found, it would compel a revision of core physical assumptions. It might open lines of thought on why ordinary matter dominates the universe despite both matter and antimatter being predicted in equal shares after the Big Bang. It could even suggest new mechanisms related to cosmic acceleration. But at present, no experimental evidence supports these possibilities. For now, they remain intriguing only insofar as they remind scientists what might change if results were someday different. Antimatter, then, serves a unique purpose in gravitational studies. It tests the edges of our frameworks where relativity and quantum mechanics do not always align. Antimatter symmetry is central to quantum field theory. If gravity were discovered to break that symmetry in some subtle way, it would spotlight the missing link between the two great physical theories of the 20th century. That is why even null results are valued. They affirm the strength of relativity while clarifying exactly where boundaries lie, ensuring that any future theory unifying the quantum and the gravitational must either preserve this equality or justify with new logic why it breaks. International collaborations continue to refine their data. In 2025, several experiments reported holding larger numbers of anti-hydrogen atoms for longer than before, making repeated tests practical. Advances in detector alignment reduced statistical noise. Each improvement closes a little more of the parameter space, checking for any anomaly in the pull of gravity on antimatter. The reports show no confirmed sign of repulsion, but the constraints grow sharper year after year. The effort now focuses on reducing uncertainties so well that even a difference of a few parts in 10,000 would become visible. What all of this shows is that science progresses not only through breakthroughs, but also through eliminating what is not possible. Confirming that antimatter appears to fall the same as matter is progress, too. It clarifies expectations, discards unfounded proposals, and shapes an ever clearer map of reality. For the public, anti-gravity may conjure images of impossible engines and hovering machines. In laboratories, it represents careful measurements of the tiniest deviations in how particles move, a test of the very structure of physics itself. This careful narrowing process matters because it keeps science honest. Experiments are designed, executed, and checked precisely so that any surprising outcome could be trusted if it appeared. The fact that no repulsion has been measured does not lessen the importance of the work. It ensures that if a difference ever does show, it will stand as a solid discovery. That is the essence of testing the limits, finding whether nature leaves room for a surprise and being ready if she does. As of now, experiments reveal no evidence of anti-gravity, but the techniques used to reach that conclusion keep getting sharper, and the questions keep guiding engineers to build better instruments. Want to know how such tiny forces can even be tested? Later, we'll sketch the traps and cooling tricks that make it possible to catch particles light enough to vanish in a blink. Testing antimatter in gravity illustrates how physics tackles its hardest puzzles. By patient refinement, by building systems delicate enough to probe what almost escapes detection, and by recognizing that even a lack of difference tells us something fundamental. The next step is to ask how these lessons fit more broadly into the unfinished picture of gravity. Because if relativity handles the stars and galaxies, and quantum mechanics handles the particles and fields, then the gap between them is exactly where the greatest mystery of all still waits. The quantum paradox. Relativity and quantum mechanics stand as the most accurate frameworks we have for describing nature. Each excels in its own territory. Relativity provides the mathematics for stars, black holes, and the expansion of the cosmos, treating spacetime as smooth and continuous. Quantum mechanics rules the microscopic, where particles behave as waves, probabilities replace certainties, and superpositions allow objects to exist in many possible states at once. On their own, neither theory fails. The difficulty comes when the two must operate together, because the mathematics refuses to cooperate. When gravity is treated quantum mechanically, infinities erupt in the equations. When quantum systems are placed in relativistic contexts, predictions lose coherence. This unresolved conflict sits at the heart of what physicists call the quantum paradox, a contradiction that remains one of the deepest open problems in science. The problem can be framed with a simple example. Imagine a particle existing in a superposition, spread across two locations at once. In quantum mechanics, that state persists until a measurement selects an outcome. But relativity tells us every piece of mass produces a gravitational field. If the particle exists simultaneously in multiple positions, does its gravitational field also split into multiple versions? Or does gravity itself force the particle into picking one definite location? Physicists cannot say. Each framework demands an answer, yet the answers they demand contradict each other. This clash explains why a unified description, quantum gravity, remains out of reach. For decades, the obstacle lay not only in theory but in experiment. To directly explore the regime where quantum rules and gravitational rules overlap, you would need energies trillions of times greater than those available in any accelerator. You would also need to probe distances far smaller than anything we can measure today. In other words, the relevant scales sit hopelessly beyond current technology. Attempts like string theory, loopquantumgravity, or hypothesized gravitons remain valuable intellectual efforts. But without data, each has lived firmly in the realm of speculation. In recent years, however, researchers have started exploring new routes. Instead of trying to access the unreachable scales directly, they are building systems to simulate aspects of the problem. One frontier involves quantum computers. Unlike classical machines, which process bits that are either 0 or 1, quantum processors work with qubits that can exist in superpositions themselves. This makes them ideally suited for modeling situations where superposed states influence one another, exactly the realm where gravity and quantum mechanics might collide. By 2025, teams were already running toy models of simplified quantum fields evolving under conditions meant to mimic curved spacetime. These models are crude, but they open a new path. For the first time, The clash of relativity and quantum mechanics can be tested not just on blackboards, but inside computational experiments. At the same time, several experimental groups propose complementary ideas at small scales, tabletop experiments designed to probe whether gravity itself can act as a quantum field. These plans use systems such as levitated nanocrystals or ultra-cold atomic condensates prepared in delicate superposed states. If two tiny masses could be entangled with one another through their mutual gravitational influence, it would be powerful evidence that gravity has quantum properties. Such experiments are extremely challenging, requiring exquisite isolation from vibrations and background forces many times stronger than gravity. Yet they represent the first realistic laboratory steps. As researchers often phrase it, if gravity can entangle objects, that would strongly suggest it behaves as a quantum interaction. For now, these projects remain proposals with long development timelines, but the fact that they are actively being designed marks a shift from abstract speculation toward attempts at measurement. These approaches illustrate how scientists are reshaping the way they study the paradox. Instead of waiting for a fantastically powerful collider that may never be built, they break the problem into smaller, testable pieces. With quantum simulations, one can watch how simplified universes behave when quantum rules are allowed to generate geometry itself, suggesting that space and time might not be fundamental, but instead emerge from networks of entanglement. With proposed tabletop setups, it becomes possible to ask whether gravity can act like other forces in creating entangled states. Though none of this resolves the paradox outright, both strategies transform it into questions we can begin to touch experimentally. The paradox itself remains blunt. Relativity insists on continuity, quantum mechanics insists on discreteness. Keep both assumptions and infinities appear, destroying predictive power. Discard either, and you lose what makes the whole edifice of modern physics work. That is why the search for answers has persisted for generations. Yet what has changed by 2025 is the sense that data, or at least data-like outputs, are finally in play. Simulations are not a full replacement for experiments, but they generate measurable results that can be checked and repeated. That repetition brings the paradox into a new form, no longer only a philosophical struggle, but one constrained by actual outcomes. The candidate theories each take distinct approaches. String theory depicts particles not as points, but as tiny vibrating strings, existing in higher dimensions that collapse down to the world we perceive. Loop quantum gravity discards smooth space entirely, replacing it with a fundamentally discrete network where area and volume come in smallest possible units. Some physicists still search for the graviton, a particle that would carry gravitational interactions in the same way photons carry light. None of these frameworks has yet achieved confirmation, and yet the very fact that computational tools now allow us to sift through behaviors, discard inconsistent models, and reinforce the viable ones is progress, unlike anything seen for decades. A striking development is how researchers rephrase progress itself. In past generations, without possible experiments, theories drifted. Now, even though no consensus solution has emerged, the discipline has gained footholds. Quantum processors let scientists compress complex equations into manageable systems and check if those systems behave stably or collapse. Entanglement-based tabletop proposals, though still in early design stages, make it possible to imagine outcomes that would decisively move the field forward. Progress in this context is not about elegant speculation, but about finding pathways where results become visible. The lesson of 2025 is that physics has tools it did not have before. Quantum simulations demonstrate how emergent spacetime could behave in restricted cases. Tabletop designs, while not yet delivering results, promise direct experimental tests within coming decades. Together, they form a two-track strategy: computation to explore toy universes, experiment to check whether gravity is truly quantum. Both add definition to a conflict that once seemed untouchable. And yet the paradox endures. Relativity remains unchallenged in describing stars and galaxies. Quantum mechanics remains unchallenged in describing atoms and fields. Where they meet, the collision still resists resolution. That contradiction is what keeps the paradox alive. But now, it feels like one contained within a problem set science can gradually work at solving. So which possibility proves correct? That gravity is fundamentally quantum, or that it demands a different description altogether? That is the question the coming generation of experiments, both simulated and physical, seeks to answer. The uncertainty may sound frustrating, but it should be recognized as a form of progress. For the first time, scientists are not left guessing in the dark. They have programs, prototypes, and simulations that steadily narrow the range of what can be true. The search for consistency between the two greatest theories continues, and each step hands back constraints, corrections, and new questions. The paradox persists, but it now looks less like a wall and more like a puzzle, whose pieces are slowly beginning to lock into place. And just as these computational and experimental tools let us glimpse the paradox in sharper detail, they remind us of gravity's character in an entirely different way. In the quantum domain, its behavior feels uncertain, elusive, perhaps even fragile. But across cosmic history, gravity shows qualities that look nothing like fragility. Its most defining feature may not be strength or strangeness, but something else entirely: its astonishing persistence through time. Gravity's infinite patience. When people picture gravity, they usually imagine something immediate and tangible: the weight of an object in their hand, a ball falling to the ground, or the steady pull of Earth keeping them anchored. These are brief, everyday encounters. What is less obvious is that gravity is also a force that operates on timescales far longer than we notice. It is weak from moment to moment, yet it never stops acting. Unlike other forces, it cannot be shut off, blocked, or neutralized. This continuity grants it an extraordinary role. Over billions of years, it gathers dust into planets, stars into galaxies, and galaxies into clusters. The scale of its influence depends not on sudden power, but on its capacity to act without pause, stretching across cosmic time. This contrast is easier to see when placed against human effort. Muscles can resist gravity in bursts, lifting, jumping, or holding weight overhead. In those instances, it feels as though muscle defeats gravity, but extend the timescale and the picture changes. Muscles tire, buildings erode, and even mountains wear away. Gravity reasserts itself endlessly, pulling material downward, reclaiming what temporary resistance once achieved. Human strength runs out quickly. Gravity simply waits. It is in this difference, seconds against eons, that its unique power emerges. Astronomy gives us a direct record of how this patience writes structure. In 2025, high-resolution images captured galaxies at very early stages of formation. These were chaotic systems, clumps of gas, scattered stars, irregular knots without the symmetry we associate with spirals or ellipticals. Yet these proto-galaxies tell us something essential. Given hundreds of millions of years, gravity sculpts the disarray into organized structures. Clumps merge, collisions redistribute material, and the chaos settles into coherent galaxies. These images show what simulations had suggested all along. Gravity does not act through sudden transformations, but through gradual consolidation that only emerges when the clock is measured in billions of years. A clearer picture comes from stepping through a single example. Imagine a diffuse cloud of hydrogen in the early universe. At first, thermal motion keeps the atoms spread apart. Gravity's pull is slight, almost negligible compared to the random jostling. But in regions where the density is marginally higher, gravitational attraction ever so slightly outweighs dispersal. Given time, that imbalance compounds. Denser regions pull in more atoms, grow bigger, and attract still more. Across millions of years, the once thin cloud collapses, compresses, and heats. Eventually, nuclear fusion ignites, producing the first stars. This transition is not sudden but cumulative, the result of countless tiny attractions adding up over immense spans of time. Other forces in nature do not work this way. Opposing charges cancel electromagnetic influence at large scales. The nuclear forces act powerfully inside atoms but diminish so quickly they vanish outside the nucleus. Gravity is different. It is weak, but it keeps working everywhere, never shutting off. This is why planets form stable systems, why galaxies acquire coherent shapes, and why cosmic filaments spread across the universe. The weak attraction that can be resisted in a single moment of human effort is the same influence that, stretched across epochs, sculpts the framework of everything we view in the night sky. The telescope images of early galaxies highlight this contrast in stark form. Side by side with modern spirals, they appear primitive, cluttered, broken, without symmetry. Yet with patience, those untidy beginnings evolve into the galaxies that surround us now. Extend time further, and galaxies themselves coalesce into superclusters. Each step in this chain emerges because gravity continues without interruption. What starts as chaos becomes organization, but only after billions of years. No other force supplies this kind of steady construction. Even the most extreme objects known, black holes, emerge from the same process of waiting. Stars form, live, and burn through their fuel over millions of years. In their final stages, gravity gradually overtakes the pressure created by fusion. What results is collapse beyond return, a region where not even light escapes. Explosions may mark the death throes of stars, but the enduring architect is still gravity. The collapse of mass on such scale reflects precisely the same patience seen in forming planets and galaxies, an outcome written across vast time rather than in sudden force. This story can be scaled down to Earth as well. Our planet took shape from grains of dust circling a young star. Each collision was minor and chaotic, yet gravity guided the sum of those impacts into a coherent planet over tens of millions of years. The land beneath us, the material we walk on, exists because gravity did not relent, patiently consolidating random fragments into a world. Life unfolds on top of this background. To us, a lifetime is stretched over decades. To gravity, this is less than a blink. The landscapes, mountains, and oceans we see are themselves resting on structures gravity took billions of years to arrange. The central lesson appearing in every example: proto-galaxies captured in 2025 images, hydrogen clouds collapsing, stars burning and dying, planets accreting dust, is that gravity works through accumulation. It does not overwhelm in an instant. It waits, and in that waiting it reshapes entire universes. Simulations back this up, and observations give us confirmation that what theory predicts is visible in the sky. The uniform gas of the early universe could have remained featureless. Instead, the patient accumulation of gravity transformed it into the rich structures of today. When we compare forces, gravity often looks like the underdog, easily outmatched by electromagnetism or the nuclear interactions in any immediate contest. What those comparisons miss is the horizon of time. Over billions of years, those stronger forces cancel or dissipate. Gravity's pull, however small, compounds without end. In that endurance lies its real dominance. Gravity's strength is its constancy, weak moment to moment, but inexorable over cosmic time. And while this steady influence explains the order of galaxies and the progression of the universe, it also underscores something more unsettling. Even with all we can describe about how it works, large questions remain unanswered about what it truly is. That uncertainty presses physics forward, toward the possibility that our current theories may not be the final word. A new physics on the horizon. Physicists are beginning to consider that the frameworks we already have might never merge into one perfect whole. For much of the last century, the quest was straightforward: force general relativity and quantum mechanics into a single theory that could describe both the vast scale of the cosmos and the fine scale of subatomic particles. The problem has always been obvious. Relativity defines spacetime as continuous, curved smoothly by mass and energy. Quantum mechanics insists that reality comes in discrete steps, governed by uncertainty and probability. Overlay both sets of rules and the equations break down. Relativity speaks in certainties about orbits and trajectories. Quantum mechanics accepts only probabilities. The moment we try to apply both at once, contradiction arises. Many now suspect that the hope of a flawless unification may be misplaced. The space being explored in 2025 reflects that shift in thinking. Instead of waiting for a single final law, researchers are developing hybrid models that borrow pieces from each framework. These efforts accept that no one theory may dominate across all scales. Some models allow spacetime to remain continuous at large distances, but treat its smallest pieces as statistical, with quantum uncertainty built into the geometry itself. Others propose that quantum states exist within curved spacetime, but do not always behave in ways predicted by classical relativity. The new direction emphasizes coexistence over a forced merger. Both relativity and quantum mechanics might yield some of their principles while preserving enough to remain recognizable. One active line of work tackles the status of determinism. In relativity, the future unfolds from the present with rigid predictability. If the initial conditions are known, the outcome can be calculated. Quantum mechanics breaks this assurance by offering only probabilities. Hybrid proposals must decide whether determinism holds at the smallest scales or whether even spacetime itself follows a probabilistic law. A few suggest that apparent determinism is just an average picture. Probed closely enough, spacetime might flicker with uncertainty the same way electrons do inside an atom. To observers like us, it smooths out into predictability, but at root it would be built from probabilities. Others favor the opposite route and argue gravity may enforce classical outcomes, collapsing quantum states into definite results. That would preserve relativity's determinism but force revisions to quantum rules. Rather than treating spacetime as fundamental, a second broad approach frames it as emergent. In this view, space and time are not basic ingredients, but consequences of deeper relationships, much as temperature emerges from the motion of molecules. Entanglement, the peculiar connection between quantum particles, could generate the scaffolding that appears as smooth geometry on larger scales. If true, then spacetime itself is not a starting point, but a product of microscopic information patterns. Such a vision would resolve the conflict by reframing it. The clash between discrete particles and continuous spacetime disappears once spacetime is no longer taken as fundamental. Though evidence is scarce, researchers are not working from speculation alone. Quantum computer simulations now allow simplified tests. In 2025, programs modeled entanglement networks and showed how they could reproduce relations similar to distances in curved space. Other groups used small quantum systems to imitate conditions of spacetime in restricted dimensions. These early results are not full theories, but they demonstrate that hybrid ideas can be probed in practice. Trial runs already show how entangled quantum states can mimic geometric features we normally attribute only to relativity. Concrete proposals illustrate how varied the thinking has become. One example comes from theorist Jonathan Oppenheim, who in 2025 presented a hybrid model where classical spacetime and quantum particles interact consistently by giving up small parts of both their rules. His framework allows limited information loss and slight deviations from strict quantum evolution in order to make gravity compatible without demanding a full quantization of spacetime. Another example comes from researchers at Aalto University, who recently advanced a program treating gravity as a gauge theory alongside the other forces of the standard model. By recasting spacetime geometry in the language used for particle interactions, the goal is to fit gravity into a framework closer to known quantum field theories. These ventures highlight how researchers are moving beyond abstract debate and exploring models with potentially testable predictions. What these efforts underline is that core principles may have to bend. Options include giving up the determinism we inherit from relativity, accepting spacetime as an emergent construct rather than a foundation, or modifying quantum mechanics so that gravity forces definite outcomes. Any of these trade-offs would alter our assumptions about how nature works. Future theories may not deliver elegance in the sense of a single perfect equation. They may instead provide a patchwork of models, each valid within its own regime, overlapping at the boundaries where previous theories clashed. This prospect shifts how physicists view their goal. In the 20th century, relativity and quantum mechanics each rewrote our description of reality, but both carried the appeal of broad, unified clarity. The next framework may refuse that clarity, offering instead a family of explanations that coexist uneasily but work where they must. Elegance may fall away in favor of pragmatism. That recognition is not a defeat. It reflects how science has often advanced, not by final answers, but by successive approximations that replace assumptions with sharper maps of reality. At the practical level, simulations and experiments are beginning to ground these conversations. Tabletop designs aim to test whether gravity itself can create quantum entanglement, which would point toward a quantum nature for spacetime. Hybrid computational models test how probability unfolds when curved geometry is introduced. Theories like Oppenheim's hybrid interaction scheme or the Alto gauge program show that even if no unifying law emerges, we may still find consistent ways to link our current physics across domains. Each attempt marks a transition from pure conceptual speculation to strategies that can yield results, however limited, in the coming years. Looking ahead, the path is unlikely to lead to a grand theory of everything. The more probable outcome is a suite of connected frameworks, messier, perhaps less satisfying, but effective across the full range of scales. We may keep relativity as our best explanation of astronomical structures, keep quantum theory for particles and fields, and develop intermediary models that handle the overlapping regions. If space is emergent, if determinism is only approximate, or if quantum mechanics requires revision, the task will be to manage these shifts without expecting that one set of equations can cover all contexts. The recognition is important because it sets the stage for how scientists interpret progress. Instead of chasing perfection, the focus is on building descriptions that function. The expectation now is modest but realistic. The universe may never allow one tidy explanation. Instead, we may end with mutually compatible theories that together cover the territory. This outlook accepts complexity as permanent. We may not get the elegant closure once imagined. What we will likely gain is something more resilient. Several frameworks that coexist, each suited to a different aspect of nature, connected but not collapsed into one. And that, in turn, leads to a broader reflection on gravity itself, because behind every unfinished theory remains the one force that continues to shape and sustain the universe, constant in its influence across every scale. In the end, what stands out is how much gravity continues to unsettle even our best explanations. It shapes spacetime, distorts time itself, and hides secrets in black holes and dark matter halos. The closer we measure it, the stranger it becomes, so the search is only getting more interesting. If you enjoyed this deep but digestible tour of gravity's strange behavior, hit subscribe and tell us in the comments which mystery you'd want us to explain next: black holes, gravitational waves, or quantum gravity. You'll also find a short reading list and source links in the video description if you want to explore further.